So in terms of determining, so I'd like to go back first to the previous. So in terms of determining the number of stages, we are to make this stepwise line on the operating lines that we have made. So we start with the XD point on the ignition section operating line, and we end on the X sub W or go beyond X sub W on the stripping section operating line. So just a short review. So last meeting, you've learned that for you to be able to plot the enriching section operating line, you need the XD and you need the either the slope or the y-intercept of this enriching section operating line. And then for the Q line to be able, so that we will be able to plot the Q line or the feed line, we need the XF and we need the slope of this line, or we need the y-intercept of this line. And the equation for this line, by the way, is this. So either you use the slope of the line or the y-intercept of the line. That way you can plot the feed line or the Q line for short. So in our problem, this is our feed line. This is our Q line, or in the example rather, in this particular example, this is your Q line and this is your enriching section operating line. Where the two intersects, that will be the point where your X sub W be connected to form the stripping section operating line. So in here, you could see that you have made 1, 2, 3, 4, 5, 6, 7. It would have been 8, but if we say 8, that this 8th step already went beyond the X sub W on the stripping section operating line. So what we do, we approximate the area in this portion here. What is this in terms of percentage to the entire area of this rectangle represented by this step? So it could be 0.8 for some, it could be 0.9 for some. So it depends really on how much you approximate this. So let's say this is a 0.8. So that would be 7.8 steps on the graphical technique, because in the second part of this set of slides on part 2 of distillation, I'll be discussing the analytical steps. So it's 7.8, but the last step class is the reboiler. So the theoretical number of stages for your column is only 6.8. So we subtract 1 from the number of steps that we have made here. Okay, that would be then our total number of steps. So 7.8 minus 1, so that would be 6.8. That would be our theoretical number of stages. As for our feed line, where our feed tray should be, it's already pointed out here on the illustration. That's where there is a change from, or that is where your enriching section operating line and your stripping section operating line actually intersects. It's part of the particular stage where your feed tray is, or it's a change of location from your enriching section operating line to the stripping section operating line. So the very first instance that you're going to transfer from one part of your, from one section of your column to another. Okay, so this is your feed plate location. The feed tray is on the 5th plate from the top of the column, or now it's the first plate on your stripping section, because your feed tray is part of the stripping section. So that's a short review of what we've discussed this meeting. Last meeting, I also tried to include this in the last part, that when the 3 operating lines, referring to the enriching section operating line, the stripping section operating line, and the Q line, if they all coincide on the 45-degree line, then what you have is a case of the total reflux, or the minimum number of stages. So the minimum number of stages will be made by simply starting from the XD down to X sub W. So in this case, it's around 3.8. So your minimum number of stages is actually 2.8 in that case, because we always subtract 1 because the last step is the reboiler. Now, this minimum number of stages is connected to the principle of total reflux. And actually, the condition in itself is implying what is happening here. So in the condition of total reflux, all the distillate and bottoms are reduced to zero. And that is, all liquid in the bottoms are reboiled, as in all, and returned to the tower as vapor, and all overhead condensed vapor are returned to the tower as reflux. So meaning, all distillate is made as total reflux liquid into your column. And this produces the minimum number of stages, the condition of total reflux. So this requires infinite sizes of condenser, reboiler, and tower diameter. So meaning in terms of design, since all the condensed vapor and all the vaporized liquid from the bottom of the column is returned back into the column as liquid and vapor, then there's no limitation as to the size of the condenser. Same thing with the reboiler and even the tower itself. Now, this gives the minimum number of trays. So the condition of total reflux results to the minimum number of trays in our column. Now, if we are to use the purely analytical manner of determining the minimum number of trays, that is, we won't use the X and Y equilibrium diagram. Though if you have that already, it's just very easy. This would be a formula that was provided by Finsky on how to determine the minimum number of trays. So in here, you have the log of xd divided by 1 minus xd times 1 minus xw over x sub w, all of which is the argument of the log, and it should be divided by the log of alpha AV. This alpha AV is the geometric mean of the relative volatility of the overhead vapor and the relative volatility of the bottom's liquid. The limitation of Finsky's method is that we should be able to determine the geometric mean of the relative volatilities of the overhead vapor and the bottom liquid. That way we can have the N minimum without having to use the X and Y equilibrium diagram. Now, we also have a condition of what we call minimum reflux, represented as R sub M. And this is when the reflux ratio is, shall I say, producing or making the infinite number of stages. So meaning at this condition, it's impossible for us to determine the number of stages for our column. So the reflux ratio that will require an infinite number of trays for the given desired separation of XD and XW. So why infinite number of trays? It will be shown to you graphically why when we speak of infinite, meaning there's just so many number of trays that it cannot be quantified specifically. So in this condition of minimum reflux, we have the minimum vapor flow in the tower and the minimum condenser and reboiler sizes. So the exact opposite of total reflux. So we have the smallest condenser and reboiler sizes for this minimum reflux condition. So take note, however, that you will have a large number of trays or stages for your distilling column in this condition. Now, the operating lines enriching and stripping line moves farther from the 45-degree line and closer to the equilibrium curve, which makes the number of steps required infinite. So if in the case of total reflux, your operating lines are all coinciding with the 45-degree line, in the case of minimum reflux, it's the other way around. So these operating lines are extending themselves towards or approaching the equilibrium curve as much as possible, intersect it, as such producing what we call as the infinite number of stages. So your minimum reflux condition is shown here. Your operating line and your stripping line together with the feed line now meet at this point we call the pinch point. So the pinch point is actually the point of intersection of your feed line to your equilibrium curve or equilibrium line. So wherever this pinch point is located on the curve, the two operating lines, the enriching section operating line and the stripping section operating line, will also meet at that particular point. Graphically, it's really common sense because if you're going to make steps here, there's no way that you can make another step here for you to be able to transfer on the next section of your column. And as such, it is known as the condition that brings about the infinite number of trays, because you can no more, or you can no longer rather account for your number of trays in this case, in the condition of minimum reflux. Now, how do we determine the minimum reflux ratio? So after you have determined from the feed line its intersection or its point of intersection on the equilibrium curve, represented by x prime and y prime here, you can substitute it in this equation together with the distillate concentration. Okay, so xd, you only need the xd and the x prime and y prime, and you will be able to determine the minimum reflux ratio. Okay, just in case the problem would be requiring for it. Now, why the minimum reflux ratio? Why the need of the concept of the minimum reflux ratio? Because our columns, our steels are designed to operate, optimize the operation most of the time. So with the other equipments for that matter. And the optimization of the number of trays, or on the size and on the, shall I say, the how tall your tower would be, is dependent on the optimum operating condition. The optimum operating condition is dependent on the minimum reflux ratio. So we need to know how to determine the minimum reflux ratio. Now, there are cases, but this is not common, but if there are cases wherein, let's say for example, you have drawn already your feed line, and your pinch point is supposed to be in here because this is where your feed line or your Q line intersected your equilibrium curve. It so happened that when you draw your enriching section operating line in this example, or it could even be your stripping section operating line, any of these two lines become tangential, or it became tangential to your equilibrium curve. So this point now is not anymore your pinch point, but your pinch point now is the tangential point where your operating line touches your equilibrium curve at that particular point only. The goal of this is, by the way, why did we move your enriching section operating line here? We tried to move it so that it will coincide with this pinch point, or with this point where your feed line intersected your curve. So that's the purpose. So since when you do that, it will go beyond actually this particular point, and you can't draw an enriching section operating line which is already beyond this tangential point on the curve. So instead of this being the pinch point, this is now your pinch point. This is now the pinch point of your column, pinch point of your column, and this will be the coordinates that you will be using. That way you can determine the minimum reflux ratio. You need the minimum reflux ratio for you to know the optimum reflux ratio. Now, speaking of the optimum reflux ratio, so based on the economic balance of the fixed cost of the tower and the operating cost, we need the minimum reflux to come up with the optimum reflux ratio. So the handbook gives us a range of value which is 20% to 50% more than the accounted for or calculated minimum reflux. So in our case, in all your computations here, we use the maximum value of 50% more than the minimum. So in all your calculation, you will determine the optimum reflux ratio based on this formula. It's 1.5 of the minimum reflux ratio. Okay, that's the end of this slide. And I would like to discuss a sample problem related to everything that we have discussed in here. So let me share that particular sample problem. Okay, you share. So this is actually a problem in the sample problem in John Couples. I just modified. I just, shall I say, merge all the question into one problem. That way I will be able to explain everything clearly in just one sample problem. So in this problem, you are given, okay, you're given a liquid mixture of benzene and toluene. So this is an ideal system, which is to be distilled in a fractionating tower at 101.3 kilopascal. So this is the operating pressure of your tower. Now the feed is 100 kilogram mole per hour and is to contain 45 mole percent benzene, the rest toluene, and enters at 327.6 Kelvin. Your distillate is 95 mole percent benzene, the rest toluene, and the bottoms is 10% benzene, the rest is toluene. The reflux ratio is 4:1, and the average capacity of the feed is, this is the average heat capacity of the feed, is 159 kilojoule per kilogram mole Kelvin. So it's the CP. I place it here. And the average latent heat, place it here also, 32,099 kilojoule per kilogram mole. So you are to use the appropriate equilibrium data that involves the table and the diagram. Okay, whichever of the two you will need. Okay, now for this problem, you are to determine the 6 things. Calculate the kilogram mole of distillate and bottoms liquid. Determine the theoretical number of stages, the feed plate location. You are to calculate the reflux ratio, that is the minimum reflux ratio. You are to determine the minimum number of theoretical plates at total reflux, and you are to calculate the optimum reflux ratio. So if all this given information is placed in a diagram for your distilling column, so this will be the diagram for your column now. And all the information are in here. So this is for the feed. This is your reflux ratio. This is the operating pressure. And I have labeled all the streams, so you will have a clear understanding of the streams that are leaving the tower and the streams that are entering the tower. So this is your liquid. That provides the boiled up vapor after it's being subjected to a change of phase in the reboiler. So only part of that. And this is your V sub n plus 1, the boiled up vapor. This is your bottoms liquid. This is your distillate. This is your reflux, LO. And this is the vapor coming from the first plate of your tower, or the topmost plate of your tower, that is being condensed in the condenser. This is your condenser and this is your reboiler. And these are the things that you are to determine. Okay, so the first part of the problem is to determine the D and the W, the distillate and the bottoms liquid. And this does not require any of the procedures that have been discussed in McCabe-Thiel, because this will just be simply material and component balance. So if you set up your overall material balance and your overall component balance based on the most volatile component, which is benzene, in this case, that's A. So this is your overall material balance, and this is your component balance. Your component balance is patterned from your overall material balance, and you just make use of the mole fractions provided in the problem. So you have 0.45, you have 0.95, and you have 0.10. And in here, you see that the W was already replaced by 100 minus D, coming from the overall material balance, giving you right away the value of the distillate and the bottom's liquid. Now, the second requirement, which is the theoretical number of stages, will need the um, equilibrium diagram. So I have, if I'm not mistaken, I'm not sure, please message me. I have already shared in Canvas the X and Y diagram for the class. In this case, to use that way, we will have a uniform X and Y diagram in this case. So let me see if I can find it here so I can share again to you. How does it look like? Okay, here it is. Let me see. Okay. So this is the equilibrium diagram that will be uniform for all of us. This should be printed in a short size bond paper for you to use during the quiz and even during the exam. So you are to prepare this ahead. That way you will have one to use just in case you will be required to do the graphical, aside from the analytical way of determining the things that are associated with the distilling column. So you have this particular diagram to use, that where you will plot your three operating lines. So I will go back to my, where was that? Okay, here it is. Okay, so in this case, you will plot the enriching section operating line first. And for that, you would be needing the distillate composition, which is 0.95. And you will be needing the enriching section operating line equation. And this was shared to you in the PowerPoint. So the R over R plus 1, XN plus XD over R plus 1. My students then find it easier to use the y-intercept of the line. That way they can plot the enriching section operating line. So in this case, you need the distillate composition and the reflux ratio. In our case, in this problem, the y-intercept is 0.9. So I would just illustrate how will you do that. So for example, this is your X and Y diagram. So you locate the 0.95, you go up and project it at this point. And then the 0.19, which is the y-intercept, you locate here because that's where this line is going to intersect your vertical axis. So your 0.19, if this is 0.2, this is 0.1. So your 0.19 is somewhere here. You connect this point to that point which you have projected here for your XD. That would be your enriching section operating line. Of course, you need not connect it really from this point up to there. So you will only try to reflect that line in this portion here. That way your graph will not be really full of lines, or your illustration will not be full of lines, because what you just need is a line. And in that case, you'll be needing 1 point on the line and the y-intercept of the line. Some of my students would use the slope, but in the case of the slope, you need to assign a new point. That way you can connect it with the point on the 45-degree line. That way you can have a line. So in that case, if you want the slope, this would be the 0.8 that you will be using. So you're done already with the enriching section operating line. So that particular operating line is this, okay? So you need not really connect like from here to there to here. Just simply start writing your line in this section, not the entire line. Okay, the next thing that you are to do is you, excuse me, you need to plot the feed line or the Q line. In plotting your feed line, you need the XF, and that's the 0.45 mole percent given, and you need the Q. This problem gives you the latent heat of evaporation of the feed, and the latent heat of vaporization rather of the feed, and you're also provided with the CP of the feed. Now in the numerator for the formula for the Q, you have HV minus HF, and we don't have this. But we try to manipulate or find an equivalent expression for HV minus HF. Now, if we will have HV minus HL, because this one represents the latent heat of vaporization, the HV minus HL, then you have to think of what expression you will add it to this. That way, the resulting expression would be HV minus HF. So you need to get rid of the HL here, which is negative. So you need to add HL, and you need to add negative HF. So you need to have this expression added to this. That way, you will have the equivalent HV minus HF in here. Because if you do the addition here, you'll get rid of the HL, leaving you with the HV and the HF. Now, the big question is, why manipulate it in this form? You have already HV and HL as the heat of vaporization, or the latent heat of vaporization. And HL minus HF could be solved based on the average heat capacity of the feed, HL minus HF, which is Cp of the feed times the boiling point of the feed minus its temperature. This one, the Cp times the quantity T sub B minus T sub F, is already HL minus HF. The difference between the saturated enthalpy of the liquid minus that of the feed enthalpy. This is it already. So since you have this and you can process this, then this will be the expression, the entire expression that will replace HV minus HF in the numerator. Now your Q then, the one that we have here, is alpha plus CPF times TB minus TF over alpha, lambda. So this one, lambda and lambda. Okay, now everything here, the lambda, the Cp, and the T sub F are all given except the boiling point temperature of the feed. So what will we use for that? So you use the equilibrium boiling point diagram, which was provided to you as an example at the start of the phase equilibria topic. So in the case of benzene and toluene, you will have this particular diagram in the case of the boiling point of the liquid. So that would be this one. You look for in this case, our feed is 0.45. No need for me to go up. So you look for 0.45 and you go up and you stop in here. Rather in here, saturated vapor line, and read this one. That would be the temperature, the boiling temperature of your feed based on the 45. By the way, class, it's 45. Don't follow that one. By the way, this is a different line. So it's 0.45, and here you go up, and if it's a saturated something, saturated liquid, it should be in here. It's about to boil in here. So 0.45, somewhere there. Okay? You have to stop in here in this particular curve, the lower curve, because this is your saturated liquid line, giving you the boiling point of your liquid. Okay. Now from this graph, you'll see that your boiling point is 93.5, more or less, because this is 95 and this is like 93. If you'll have the 0.45 in here. Okay. So you have now the boiling point of your feed. Now with that known, then you just have to substitute, you change or you convert this relative temperature to absolute temperature. That would be 366.7, rounding it off, using the 273.15 added to 93.5. And this one is for the temperature of the feed in Kelvin as well. So this is the lambda, and this is the Cp, this is the Tb minus the Tf, and this is the latent heat of vaporization, giving you a Q which is 1.195. How will you make use of this Q? So you use it in this equation of the Q line, which was also shared to you in the PowerPoint. So in here, you may use the slope again of the feed line or the Q line, or you may use, it's easier, if I were you, it's easier to use the y-intercept. This time, it's negative. So you need the mole fraction of the feed, and you have the Q as well. So you'll need this value to plot on the lower part of the X and Y diagram. Anyway, what you just need is just portion of the line that is right on the this one, right on our diagram on the upper part of the 45-degree line. So if your negative is somewhere here and you're going to connect it to the point 45 right on the 45-degree line, you just start somewhere here, then going there. Not that you will really draw an entire line from the negative part in here going up. So you just need the point of intersection of this Q line and this enriching section operating line, because that's where your stripping section operating line should be connected to from the X sub W. So in that case, it's already explained here that in plotting the stripping section operating line, you need to connect the XW, which is point 10, to the point of intersection of the two lines previously plotted. So your number of steps minus the reboiler in this case is 6.6. The feed tray is introduced on the fifth plate of the column. Actually, this is the exact graphical solution of the problem using McKeith-Thiel. Okay, now the next question is, you need the minimum reflux ratio. So for you to be able to determine the minimum reflux ratio, you need the X prime and the Y prime. If you go back to the one that you have drawn in here, this is the point. You have to read the X prime and the Y prime here. So the XY and the Y prime for this problem is 0.49 and 0.702 respectively. So substituting to the formula that was shared to you for minimum